Last time, we used row reduction to find A inverse. Today we stop halfway through elimination and notice something useful. A can often be written as LU. In other words, Gaussian elimination secretly gives a factorization. Very considerate of it, after all the arithmetic trauma. LU decomposition means writing A as L times U. U is the upper triangular matrix produced by ordinary elimination. L stores the multipliers we used during elimination. For the moment, assume no row swaps are needed. Row swaps are useful, but they barge into the notation wearing muddy boots. Here is the example we will factor. Take A to be this 3 by 3 matrix. We will perform forward elimination to get U, and record the multipliers to build L. The first pivot is 2 in the top left. To eliminate the 4 below the pivot, subtract 2 times row 1 from row 2. To eliminate the 8 below the pivot, subtract 4 times row 1 from row 3. After those two operations, the first column is cleared below the pivot. The numbers 2 and 4 are not garbage. They will become entries of L. Finally, arithmetic has a recycling program. Now use the second pivot, which is 1. To eliminate the 3 below this pivot, subtract 3 times row 2 from row 3. This gives the upper triangular matrix U. So the elimination part found U. We are halfway to the factorization. Not just halfway to another spreadsheet headache. Now build L from the multipliers. Put 1s on the diagonal of L. Then place the multipliers 2, 4, and 3 below the diagonal. This gives L. It stores the exact numbers used to eliminate entries under the pivots. Those multipliers are the memory of Gaussian elimination. Slightly dramatic but accurate. Let us check that L times U gives back A. Multiplying L and U gives the original matrix. Therefore A equals LU. The factorization did not appear from blind faith. It came from tracking exactly how elimination transformed A into U. Now let us explain the logic using elementary matrices. Each elimination step is left multiplication by an elementary matrix. The operations that subtract 2, 4, and 3 times earlier rows turn A into U. Now reverse those operations. That writes A as a product of inverse elementary matrices times U. That product of inverse elementary matrices is L. So A equals LU. No trusting me required. Which is good, because that would be a terrible mathematical standard. Why bother with LU decomposition? If A equals LU, then solving AX equals B becomes solving LUX equals B. Set Y equal to UX. First solve LY equals B, then solve UX equals Y. Both L and U are triangular, so the two solves are easier than starting elimination from scratch. This is especially useful when the same A is used with many different right-hand sides. Repeating elimination every time would be a lifestyle choice. And not a good one. But not every matrix cooperates without row swaps. For example, this matrix has a 0 in the first pivot position. We swap the two rows using the permutation matrix P. Then PA has a usable first pivot. In general, with row swaps, the clean statement is PA equals LU. Let us say what PA equals LU means conceptually. P records the row swaps. L records the elimination multipliers. U is the upper triangular matrix left after elimination. So PA equals LU means, first reorder the rows, then do the same LU story. Let us summarize before the letters L, U, and P start demanding separate dressing rooms. Forward elimination gives U. The multipliers used during elimination build L. If no row swaps are needed, A equals LU. If row swaps are needed, we record them with P and write PA equals LU. Next time, we can decide whether to continue with computational tools or finally unleash determinants. A grim crossroads, but a mathematically useful one.